Hello, my name is Babak, and I will talk about CO2 conversion in the plasma state. Now, diverse energy resources like sustainable energy, hydrocarbons, nanogenerators, and other harvesting units have to be developed in order to meet the requirements of our modern society. Now, this means that diverse energy processing centers will be developed where different energy modules would have access to all sorts of feeds and thermodynamic conditions. And whenever we have hydrocarbons, if we want to produce electricity out of hydrocarbons, there will be CO2 emissions, and therefore the CO2 has to be captured and either injected into fields, or it could be converted, CO2 converted into valuable products or other energy forms. Now, the CO2 conversion for hydrocarbon fields is worthwhile because if you consider the heating value of hydrocarbons, the energy that's required to convert CO2 is less. So less amount of energy is required to convert the CO2. So it is worthwhile. If it wasn't worthwhile, if you had to use more energy to convert CO2 into a valuable product, we would have not even used the hydrocarbon fuels in the first place. But since we are able to uh, 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 convert CO2 into other forms with a less amount of energy, it's worthwhile to do that. Now, and the CO2 conversions, there are many of them. There are many methods, and it all depends on the available feed and the available thermodynamic states that you might have in that energy processing center. And obviously, catalysts and nanostructures are also used to decrease the activation energy and favor the desired product. And for the conventional method, the thermal conversions, we have direct splitting, which is the endothermic process. And it's not possible unless you use energy resources from sustainable sources. Then there is one way to take care of this problem is to use hydrogen containing co-reactants to take advantage of the less negative Gibbs free energy. So this will make the reaction less endothermic, so it'll be more favorable. And examples of this type is like hydrogenation, where the co-reactant is the hydrogen, and in dry reforming, in which the co-reactant is the methane, and there are others like artificial photosynthesis, where we use water as the hydrogen-containing co-reactant. And there are other types too. There's the electrochemical conversions and there are photochemical conversions. There's biochemical conversions, and it's just there's a lot of different kinds of CO2 conversions. And like in one option, you can if in that energy processing center you have heat available from, let's say, some combustion or some exothermic reaction nearby, and you have the CO2 and other gases. And if you use a selective type of catalyst and careful design, then you can have carbon nanotubes or carbon nanofibers as a product, while you're in the CO2 conversion process for chemical vapor deposition. Deposition method is being used. So there's a lot of different techniques for CO2 conversions, the converting CO2 into a valuable product, and it all depends on what's available in that diverse energy processing center of the future, or what is available. Now, suppose you want to operate with a lower operating pressure and temperature, and you choose the plasma state for the CO2 conversion. Plasma state, as you're well aware, is the ionized gas state, and for this purpose, you would apply electrodes to produce produce electric field, and they apply electrodes on a reactor, both sides of the reactor, and you have insulating dielectric between those electrodes, and in order to operate CO2 conversions that use the plasma state with the low operating pressure and temperature, the electric field that's produced has to be such that the average electron energy, the maximum should be like 10 electron volts. Now, so let's see how it operates. So in the case of CO2 conversion, we have a ground state CO2, and when we want to operate it in plasma, in this low pressure and low temperature plasma state, it's subject to perturbed vibrations and other degrees of freedom. So basically, CO2 breaks its bond, and this it leads to vibrationally excited molecules, ions, and radicals. And now there are things that we have to be careful, because when we're producing ionized gas state, ionized CO2 gas state with the maximum 10 electron volts average electron energy. It's called non-thermal or cold plasma, or non-Maxwellian type of plasma operation. That's because the ions and electrons they have, and other components, that have different kinetic energy or temperature. But what happens is that obviously you need catalysts, because the catalysts, they provide reaction pathways in order to have the desired endpoint, and in order to promote a surface reaction, just like other types of it's just a normal procedure for catalysts. And the location of active sites is very important, because we are operating the CO2 conversion in the with the like a in a non-thermal ionized gas state. So what happens is that when we have maximum of 10 electron volt average electron energy, in order to have a lower operating pressure and temperature, we have to the active components they have like a short life cycle. They have a short life cycle, so location of active site is very important in order to promote the surface reactions. So a lot of design, very critical design for the catalyst. And now in the CO2 splitting in plasma state, like the conventional one, you can have the normal direct splitting. Obviously, it'll be easier with having this being in the ionized gas state. And there is we have the hydrogenation option, with the co-reactant is just hydrogen, if hydrogen is available in that energy processing center. And there is also dry reforming option, where you have the methane as the co-reactant, just like in the conventional case. And if carbon monoxide is produced, we can use Fischer-Tropsch process, which, as you're all aware, is an exothermic set of reactions that you can use that to produce synthetic fields. So again, we can't say like one method is better than the others in CO2 conversion. It all depends on what's available. If you have a setting where you have access to high pressure and temperature, or you have access to certain type of feed, and it all depends on how this diverse energy processing center works out. Maybe you have access to sustainable energy sources, that you have a lot of access to electricity, and it's hard to tell. We can't the CO2 conversions. It all depends on what's available at hand, and they're all good, and in the sense that with comparison to the energy that's produced by the hydrocarbon fuel, the energy that's required to convert CO2 into a valuable product is less amount of energy is required for that purpose. Well, thank you for listening to my presentation, and I hope you enjoyed it.